welcome to Easy Elim Learning Simplified. My name is Ruth, and today we're going to be discussing the topic structure and bonding. And you're going to be doing metallic bonding. Metallic bonding is one of the bonds that is the last bit of the structure and bonding. So previously we talked about ionic bonds and covalent bonds. You can go back and check out the videos on that. So for this lesson, you look at how a metallic bond is formed, and then you look at the properties of a metallic board and you get to do a few questions in regards to what you're going to discuss. So a metallic board is a board formed due to the electrostatic attraction between the positively charged nuclei and the negatively charged delocalized electrons that hold the atoms together. So we have the positive nuclei and the negatively charged localized electrons, and it's specifically the localized electrons, the ones that are on the outermost energy level. So when a metallic bond is formed, it's usually formed between many atoms surrounding one atoms. And what happens, because there are so many atoms, each of them is contributing a valence electron. So these valence electrons are usually attracted to the positive nucleus. So it behaves, it's in like a positive nuclei of different atoms are immersed in a sea of mobile electrons. So this is what the structure would look like. So we pick the circles as the positive nuclei, and each positive nuclei represent one atom. Let's say this metal was having one delocalized electron. So there's going to contribute one electron. So let's add a few more positive nuclei, and we add a few more electrons as well. So these electrons are always in a constant motion. They can be attracted by different nuclei. So it looks like the positive nucleus is immersed in a sea of mobile electrons. So because the electrons are always like in a constant motion, like they're always moving about, so they can be attracted, an electron of one atom can be attracted to the positive nucleus of another atom. So that's how the metallic bond is formed. So the sea of mobile of electrons are said to be delocalized, which explains the ability of substances with metallic bond to conduct electricity and also heat. And the pattern of the positive nuclei in a sea of electrons is repeated many times throughout the metallic structure, leading to a giant metallic structure. And the only structure is due to metallic bonds. So that's how the metallic bonds are formed, and this happens only in metals. And the more delocalized electron a metal has, the stronger the bond, because most of the delocalized electrons will be attracted to more nuclei, making the metallic bond to be stronger. So some of the properties of this bond are they have very high melting point and boiling point. So because of those strong bonds throughout the structure, there is need for like a lot of heat to break them. And the strength of the metallic bond usually increases with the increase in the atomic size, with the decrease, in the atomic size, as well as the increase in the number of the localized electrons. So if you were to look at like down a group, we know down a group, the sizes usually increase. So when you are looking down a group, we do not consider the delocalized selections because down a specific group, the number of delocalized selections are equal. Let's say we pick group 1. Group 1, all elements in group 1 have one delocalized selection. So down the group, the atomic size is increasing. This will cause them to have weaker metallic bonds down the group. So that's the reason why the melting point and boiling points usually decrease down the group. But now when you look at the localized selection, it usually applies a lot when you look at across a period, which we are going to discuss later on in another video. You can go and check it out. So when you look at across the period, the number of energy levels are the same, but what changes is the outermost electrons. They are being increased as you move across the period. So the more delocalized electrons a metal has, the stronger the metallic bond. For example, when you talk about sodium, magnesium, and aluminium in period 3. Sodium has one delocalized electron, magnesium has two delocalized electrons, aluminium has three delocalized electrons. So it is automatic for you to realize that aluminium will have the highest melting point in comparison to the two other metals, and hence, because it has more delocalized selection, it has nothing to do with the atomic sizes. So the atomic sizes are affected by donor group, like the sizes affect the metallic bond donor group, and then the localized electron affects the strength of the bond across a period. So metals with smaller atoms and more delocalized electron will tend to have stronger bonds, hence high melting point and boiling point. This explains why the melting point of metallic elements in period 3 elements increased from sodium to aluminium. I've just explained that. So they are also good conductors of heat, which comes back to the delocalized electrons we have just discussed about. And we said because the more delocalized electron an element has, the more it will be good conductors of heat and electricity. So the electrical conductivity of metals increases with increase in the number of delocalized electrons in each structure. This explains why aluminium is a better conductor of heat and electricity more than magnesium and sodium. And when you're answering this question, because it comes when you're asked about aluminium, make sure you specify the number of delocalized electrons for magnesium and the delocalized electrons for sodium and aluminium when you're answering. So this is just an overview. You can see lithium, sodium, potassium, these all have the same number of valence electrons. And you see now where the difference comes in with the melting point or the strength of the bond. You see potassium has the largest atomic radius, so you see the melting point is very low. So lithium is the smallest because this is across and down a period. Down a period, the size matters. So the smaller the atomic size, the higher the melting point and boiling point. The larger the atomic size, the lower the melting point and boiling point. When you look at magnesium and aluminium, you can see it across the period. So you can see because aluminium has more delocalized selections, you can see how the melting point shoots and the boiling point. And you can see it's more than magnesium. But you can see their conductivity is really good. And we say that metallic bonds or metals usually conduct electricity in solid state and also in molten state. This is because we don't talk about ions in metallic bonding, we talk about the localized selection as you've seen when we were discussing. So let's do a few questions. So the table below gives the same information about electrical conductivity and is like unlikely bonding in substances N, P, and Q. Complete the table by inserting the missing information in spaces numbered 1, 2, and 3. So you have substance N, substance 1, the board. This substance conducts electricity in molten state, and it also conducts in solid state. We just said that this is going to be metallic bonding. Metallic bond is the one that substances with metallic bonding are the ones that conduct electricity both in molten and solid states. And remember, their particles that conduct is the delocalized electrons. In both cases. Then when you look at substance P, it does not conduct electricity in molten state, but it conducts electricity in solid state. So the one that behaves this actually is a giant atomic structure, the graphite. So we will say it's the covalent body. But if you were asked about the structure, we would say it's the giant atomic structure. And this is actually the mode that behaves in this manner. It usually conducts in solid states and it has also delocalized electrons. And then substance Q does not conduct both in molten and in solid state. Also, the bonding in this case is going to still be covalent, but it's a molecular structure. So we write covalent. bond. They all have covalent bond. The only difference is it's a molecular structure. So molecular structures lack delocalized electrons or mobile ions. That's the reason why they do not. We also have ionic bonding, which we also discussed. You can go and check it out. So another question is a diagram below is a section of a model of the structure of element T. So you can see element T, that is metallic bonding. Say the type of bonding that exists in T. So this is metallic bonding. And then the next is in which group of the periodic table does element T belong? So when we are considering the group in which element T belongs, we are considering the delocalized selections. So whenever you are given such a structure and you want to find out the delocalized selections, what you do is you calculate the number of nucleus or the protons on the positive nucleus versus the number of electrons. If they are equal, it means it's one valence electrons. If they are double, it means it's two delocalized electrons. If they are triple, the number of electrons are triple number of nucleus, it means it's three delocalized electrons. This is what I'm meaning. So when you count this nucleus with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it means we have 12 atoms. Let's count the number of the localized electrons present. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you can see the number of electrons and the positive nucleus are equal. So it means for every atom, there's one delocalized electron. So this tells us that each atom has one delocalized electron. So this is group 1. So you will go ahead when you are told to give a reason, you will say that the number of the nuclear charge is 12 and the number of electrons are 1. So for every atom, there is one electron attached to it. Another question is study the table below and answer the questions that follow. So you have that table substance U, X, W, V, and Y, and their melting point and boiling points. And then you can see their conductivity in solid and in liquid. So U is a good conductor in both cases. X, W, and V and Y are not good conductors in solid state, but they are good conductors in liquid state. So the first question is which substance is likely to be a metal? Explain. So the one that is likely to be a metal, first of all, you notice metals conduct electricity both in solid and liquid state. We would want to go to the melting point and boiling point, but that will not be like a specific reason why it's a metal. It's a metallic bond. So what we do, the one that gives us the biggest clarity is the conductivity. So the metal is going to be U, and then the explanation is because it conducts electricity in solid state and liquid state. And then which substance is likely to be a liquid at room temperature? So when you talk about liquid, it means this substance has moved from a solid to a liquid. It has undergone melting. So we want to look at the melting point. And the melting point needs to be lower than the room temperature, because you want this substance, by the time it reaches to the room temperature, it has already turned into a liquid. So it needs to be lower. And the approximate room temperature is 21 degrees Celsius. Other books, they talk about 27 degrees Celsius, but in this range. So when you come back to your metals or substances, you go to the melting point, that would be our focus, and you take any melting point that is below the room temperature. And we're not going to take the value V. Yes, it's below the room temperature, but the temperature is, so the melting point is so low. So the value that we are going to take is going to be W. You can see it's 5 degrees Celsius and it's below, just below the room temperature. Which of the substance is likely to have the following structure? Simple molecular. So simple molecular are poor conductors of electricity and they have very low melting points and low boiling points because of the weak van der Waals forces. So the one that has the lowest melting point and boiling point in this case is going to be V. And you can see also in the conductivity, it's poor in solid, but it's good in liquid state. So we are still going to pick V because of the low melting point and boiling point because of the van der Waals forces. Giant atomic structure. So giant atomic structure must have a very high melting point and boiling point, but they're not good conductors of electricity in liquid state. Some of them might be good conductors in solid state, like graphite. So the highest that you're going to pick here is Y, because it cannot be U, because we said U is a metallic bond. And that brings us to the end of metallic bonding. So watch out for the next session as we are going to be tackling period 3 elements. See you then.